So today is December 5th. So if you want to put the date in there, 12/5. If you want to put your name up here as well, that might not be a bad idea in case it goes missing so we can get it back to you. All right. So today we're starting off by graphing radical functions. We'll then talk about transformations of radical functions. We'll then talk about graphing parabolas, but different types of parabolas than you've seen before, and graphing circles. So there's going to be quite a few things in today's notes. However, it won't take very long to get through, mostly because the graphing portion is a lot of it's going to be taken care of using a calculator. So let's take a look. So here we go. A radical function, that's our fill in the blank here, radical function. Has the independent variable x in the radicand. So basically, anytime, heads up here, guys, make sure you have a pencil. Anytime you have your variable under your radical symbol as part of the radicand, that would make it a radical function. We're going to be focusing today on square roots and cube roots, like I mentioned. And so going back to what we talked about, like at the very beginning of the school year, the idea of parent functions. And in fact, I'm actually teaching Algebra 2A again this trimester, and we just started talking about parent functions and transformations. So we get to go back to that today. So a parent function is the most basic form of a particular type of function. So if you're talking about a square root function, the most basic form of that would be f of x is equal to the square root of x. There's no other numbers with it. It's just the square root of the variable. Same thing with cube root, just the cube root of the variable. That is the parent function. Both of these functions look exactly like that. And if we think about going back to what happens when you take square roots and cube roots, especially when we were solving them, where x could have maybe, it could have a positive or a negative. It might have 0, but it can't be negative. And that's why this one doesn't end up going into the negatives at all, is because you can't square root a number and have the value be a negative number. So therefore, we don't have that. It just doesn't work. And so that's why we start at 0. So the domain and the range are both greater than or equal to 0. So every value of x is greater than or equal to 0. Every value of y is greater than or equal to 0 because of that. Now over here, with cube roots, we learned that you can have positive and negative radicand values and still take the cube root of those values. Therefore, negative numbers work just as well as positive numbers do. And so the domain and range here will be all real numbers for any of them, because it's going to go left and right forever, and it will eventually go up and down forever as well. So what we're going to be working on is, unfortunately, these didn't print all that great. The domain and range portion to write these in are actually at the top of the next page, which is super annoying. We can just probably fill them in at the bottom of this page, though, just to keep them together. So we're going to be looking at these two graphs here, and we're actually going to start off not by using our graphing calculator to look at it. We're actually going to start off by making a table of values, kind of the old school way of making a graph. You've all done that plenty of times. So how many numbers do we generally need to make a parabola? Do you remember? How many values of x do we usually need to make a parabola? I see 3, I see 4, 5. It's 5. So for parabolas, we always use 5 for parabolas because we need the vertex. That's the middle point. We need 2 on each side, but if we only have 2 on each side of the vertex, we wouldn't know if that's a V-shaped or a U-shaped graph. So for that reason, we need 2 more after that. So a total of 5. So here we're going to do the same thing. Use 5 points. Over here, let's see, graph using at least 5 points. Preferably more if you can fit that on. So we're going to start with 5. We'll just start with 0 through 4 for our values of x. We'll plug in, figure out values of y. So I'm going to set up our table over here. We'll just say here's x, here's y. Or if you want to call that f of x, that's fine too. F of x and y are relatively interchangeable. So let's start with 0, and then 1, 2, 3, and 4. We might end up going further than that. We probably will go further than that, just because of the value that is being multiplied by x in our radicand here. So let's see. Underneath the radicand, 1/4 times 0 is 0. The square root of 0 is 0. All right, so we got the point 0, 0. So on your graph, locate 0, 0. All right, then we're going to go ahead and plug in 1. 1/4 times 1 is 1/4. What's the square root of 1/4? That'd be 1/4 squared. 1/2. Yeah, we're going the other way. So 1/2. We can call that 0.5. That's fine. So go over 1 and then up 1/2. Put a point. 1/2 is an approximation here. If we plug in 2, that would be 2/4 or 1/2. And the square root of 1/2 is not going to be a nice decimal. So I'm going to grab a calculator and type that in. We're going to go to math, down to the, well, I don't even need to go to math to get the square root. So square root, and then math, go over to fraction and 1/2. There you go. So that'll be about 0.71. So 0.71, we'll start drawing some lines in between here just to make sure I can separate those and look at them easily. If we plug in a 3, that would then be the square root of 3/4 because 3 times 1/4 is 3/4. So I'm just going to copy and paste. Go back to my numerator, replace 1 with 3 and the denominator with 4. That's going to be about 0.87. Let's see. So 0.71, maybe about here, 0.87, right about there-ish. So it's going up about like that so far. If we plug in 4, 1/4 times 4 is 1. What's the square root of 1? 1. All right, so 4, 1. If we keep going, 5. Let's see how many more we can fit on here. So if we type in 5, that'll be 5 times 1/4, which is 5/4. So I'm just going to go back up here, copy it, paste it, go back to my numerator, replace the 3 with the 5, 1.11. Which will be about right there. Let's see, next, how about 6? 6/4 would be 3/2. So let's see, the square root of 3 over 2 this time. About 1.22, so 6, 1.22. All right, about almost a quarter of the way up. Kind of where we're at now. 7 would be 7/4, so the square root of 7/4. Replace that, go back, replace 3 with 7, 2 with 4. 1.32, so 7 would be 1.32. That's not much higher, about right there. 8/4 would be 2, right? So that'd be the square root of 2. So I'm just going to type in the square root of 2. That's 1.41. A little bit higher there. And you can see it's starting to almost level off a little bit. 9, let's see. Yeah, we got room for 2 more. So let's do 9. 9/4 will be our next one, and then 10. We'll just do all 10 of these, just to give us a really good idea about what we're looking at. All right, so let's see. 7/4, we'll go to 9/4 instead. Square root of 9/4 is 3/2. That makes sense because the square root of 9 is 3 and the square root of 4 is 2. So that's 1.5, exactly 1.5. That's halfway right there, 1.5. And then the last one, 10/4 would be 5/2. So let's see, square root of 5 over 2, 1.58. All right. That's a little bit higher still, 1.58. Now you can see that it goes up by 1/2, then it goes up by about 0.2, and then it goes about 0.16, and then 0.13. So it's still increasing. Every time it's increasing, but every time it's increasing by a little bit less each time, right? That increase is like getting less and less as we go. So as we draw our square root graph, it's going to look about like that. These are not going to be perfect because, well, we're not calculators. So it can't quite look as perfect as the calculator is going to show it. But once we have that on there, let's go ahead and get to our y equals menu. Go ahead and clear out any functions that are in there already. And let's just type in the square root of 1/4 times x. And I said 1/2. I don't want 1/2. I want 1/4. There we go. All right. So the square root of 1/4 x. And if we graph that, that looks about the same. In fact, we could get our table of values from the table that's on the calculator here. So We went 0 through 10, and so if you look over here, those are the values that we had. 0, 0, 1, 1/2, 2, 0.71, 3, 0.87, 4, 1, 5, 1.11, and so forth. So all those points there are exactly what we figured out here. So let's talk about this for a second. We're going to identify the domain and the range. So we're going to say d dot dot every x value. What are our possibilities for x values here? What's the smallest x value on this graph? 0, and they're all greater than or equal to 0, right? We definitely have equal to 0 because that was our initial point here. So it's going to be the same as this square root one up here, where the domain was x is greater than or equal to 0. So we're going to say x greater than or equal to 0, and then the range. What about the range? What's that? It's not going to be all real numbers because it doesn't go negative, right? But it'll actually be the same as this. It won't though, because you can't square root a negative. Yeah, it'd be imaginary. Yeah. So on a regular graph like this with real numbers on our graph, we're not going to be able to get negatives. So we're just going to say the same thing. X is greater than or equal to 0. All right. So the next one, we're going to take a look at the, let's see, -3 times the cube root of x. And we'll see what happens with that one. So we're just going to do one more of these. This time, we're going to use values that are going to be a little bit more useful in terms of cube root values. So let's set up an XY table off to the right side here. And cube root values would be like what? 1 is a cube root, 8 is a cube root, right? So I'm going to say we should start with, let's go from, let's say -8. We'll start with that one. Because the cube root of -8 is -2. And -2 times -3 is 6. So that gives us a point of -8, 6. So if we go back to -8 and up to 6, we'll put a point there. Hopefully that makes sense. What's the next cube root that is smaller than 8? Or I guess bigger than -8. Now you start from 0. 0 cubed is 0, right? 1 cubed is, what's 1 times 1 times 1? 1. All right, so that's the other one. So we'll go to -1 now. -1, because we're starting with the negatives. So the cube root of -1 is -1. And -1 times -3 is 3. So we have the point -8, 6, and we have the point -1, 3, which is going to be here, because our scale is going by 2 in each direction. So it's going to be kind of hanging out like that. And then let's go with 0, which will just give us 0, 0, 0. And then if we go into the positives, we'll say 1. If x is 1, the cube root of 1 is 1. 1 times -3 is -3. So that's 1 -3, which is here. And then if we go with 2, 8. The cube root of 8 is 2, and 2 times -3 is -6. So that'll be the point 8, -6, or -6 right there. And that's 5 points. That's enough to see kind of what's going on here. So this is going to be kind of our S-looking curve that we had. I'm going to try to get the middle of the shape going first. And then I'll connect them up here. About like that. And then this one will come down about like that. So our graph should look something like that. And we're just going to talk about the domain and range real quick on this one, and then we'll move on. So in terms of graphing, just straight up graphing these things, this is about how you can do it. Now, with square roots and cube roots, if there are no numbers other than just the variable underneath here, it's not a bad idea to choose perfect squares and perfect cubes as your values of x. That way, you know you're going to get whole number values for y as well. Just makes things a little more convenient, especially if you have room for it on your graph. Okay, so domain and range. What's our domain here? All real numbers, yeah, because this one's going left and right forever. So we can just do the symbol for real numbers, the double vertical line, capital R. And then range, what about range? All real numbers. Yeah, it's going up and down forever as well. So domain and range for those both all real numbers. Cool. So for straight up graphing, that's about it. Things can change depending on if you're adding or subtracting or whatever else, but you can deal with that using your calculator to get the points that you need. Questions there before we continue? So most of the time, make a table of values. You need 5 points at minimum, and then you can go from there. All right, turn the page. Now we get to refresh ourselves on all of our transformation rules that we learned way back in Unit 1. And the nice thing is, the transformation rules for radicals are the same as the transformation rules that we have for constants, for linears, for quadratic, for absolute value. Those are all the same here. So just as a quick review, I want to make sure everybody is remembering how these things work. I'm going to start with vertical. Anything that is happening vertically, so vertical translation, a reflection over the x-axis, like this one here, over the y-axis is different. So vertical translation, flipping over the x-axis, that would be a vertical reflection, a vertical stretch or shrink. Every single one of those things is happening to every part of the function except for where the value of x is. So it's happening outside of any groups. Anytime it's a vertical change, a vertical translation, it's happening outside of any kind of group. So that's why it's showing here with a vertical translation, move it back up, the k is outside of the group where x is. Same thing here. When you reflect it across the x-axis, the negative is outside of where the group with the variable is. It's out here. With a vertical stretch or shrink, this a is multiplying by f, which is outside where the group is with the variable. So anytime you are applying a vertical transformation, it is happening outside of whatever group it is. And in this case, our groups are going to be the radicals. So if you take a look here, if you add 7, if you go up 7 units, we're adding 7, but we're not adding it to the inside or underneath the radical as part of the radicand. With a downward shift, same thing, the -1 happens after the radical. If it is a horizontal translation, that is happening within the group. This is happening to the input value. So the other way you can think of it is horizontal translations or transformations happen to the input value, x. Vertical transformations happen to the value of y or the function value. So every other part except for the group. So the other thing about horizontal and vertical is that vertical happens kind of the way you would think it would, right? Plus means up, minus means down. Greater than 1 means you're stretching it, you're making it thinner basically, and then a fraction multiplying by a fraction is a shrink or a compression, which makes it wider. Now, when you're thinking about horizontal, not only is it happening inside your group, it's also kind of the opposite of what you would expect, because here, this says x minus h. So if h is positive, if you're moving it, you know, +4, you're moving it 4 in the positive direction, or you're moving it 2 in the positive direction, it's going to appear as a minus in your function because of the way the function works in the first place. That formula says x minus h. Therefore, if you subtract a positive, that means you're still moving to the right because h is positive. Even though it shows a minus in the function, the value of h is positive, which means you're moving it in the positive direction on the axis. So those are the rules that you learned back in units 1 and 2, chapters 1 and 2. We're going to be working with those quite a bit today. So let's head on down. I'll keep referencing these as we go over stuff. So we're going to describe each transformation of f represented by g. So we have our f of x function and then our transformed function g of x. You're going to describe it. And then it also says the graph, but the graphs are already here, so we don't need to worry about that. So what I'm going to do is I'm going to get some coloring going here. And let's see, I'll do red for the parent function because that's just the parent function of the square root of x. And I'm going to go with blue for the transformation function g of x. I'm just going to highlight those down here. So f of x, it tells us, is this one. I just find that things are easier to see if they have different colors to them, so I'm just going to do that. You're welcome to highlight or do whatever you want, or nothing. If you don't want to put anything on there, that's fine too. So a description here. We have subtraction within the group under the radical. We also have addition outside of the radical. So what kind of transformations do we have here? Who can tell me? What's that? We're going to the right 3. Yep, -3 here. So if you look up here, if you're subtracting, that's however many units to the right. That's exactly it. And the reason why I'm going to keep coming back up here is you can always go back to this to see what's actually happening. If you forget, come back to this table. So so it's a shift. Let's do bullet points, shift 3 units right. What else? 4 units up. Good. So shift 4 units up. And I mean, that's, I think, pretty clear, because if you can see where it starts and where it ends, right 3 up 4, right? You can double check that on your graph as well. It's not too much different. The domain and range, though, are going to be a little bit different. So let's talk about those for a second. At least, I mean, we're going to need f of x and g of x on here. So f of x is there. We'll have to write g of x underneath it. F of x is just the standard parent function domain and range. So that's x is greater than or equal to 0, and range is also x is greater than or equal to 0, because that's the parent function. How about g of x, though? What's our domain? What are our x values here for g of x? Yeah, x is greater than or equal to 3, because it moved 3 to the right. So now every x value is at least positive 3. How about the range? Yeah, every y value now has been moved up by 4. So everything on the y-axis. I don't know why I wrote x is greater than or equal to 0 for the range there. That should be y is greater than or equal to 0. Y is greater than or equal to 4. All right. Awesome. I'm going to put g of x for the next one as well. Let's just go and get the domain and range on for f of x, because the parent function of the cube root of x is just going to be all real numbers for each, so we can put that in there. Then we'll head back and we will describe the transformation or transformations that are happening. Yeah, let's see. So I'm going to get, let's see, red for the regular cube root of x. That's going to be that one there. So f of x, there's our parent function cube root. And then g of x, go blue again. There's that. All right. G of x right there. Cool. All right. So let's see. Annihilate, I heard you say reflection. Across which axis? The y-axis. Good. So a y-axis reflection is happening here, because if you see negative under your radical, that's going to be reflecting across the y-axis, which basically means it's gone from this to this. So it's flipping across this way. So that would be y-axis reflection. Okay. What else? What does that 8 represent? Take a look for a whole number next to the x under the radical in that chart up there. So it's a horizontal shrink, good, by a factor of close, 1/8. Yeah. So if you take a look here, if you multiply in the group, in this case, the group is under the radical, 3 times x, 3x. This is a shrink. So it's a horizontal shrink by a factor of, it's the reciprocal, 1/3. This is another example of where a horizontal change is kind of the opposite of what you would expect it to be. If it's a vertical stretch or shrink, a vertical stretch by multiplying by 4 is just a vertical stretch by a factor of 4. If you multiply by 1/5, that's a vertical shrink by a factor of 1/5. The numbers match up exactly. 4, 4, 1/5, 1/5. However, when we're talking about horizontal, kind of like the plus minus felt opposite in terms of the directions moving left or right. Same thing happens here as well when we're talking about a horizontal stretch or a horizontal shrink. And the reason for that is, if you think about a horizontal shrink, Horizontal shrink basically means it's getting closer from the x-axis to the y-axis. So a horizontal shrink functions similarly to a vertical stretch. So we've got a horizontal shrink by a factor of 1/3, and because we're multiplying it, that functions a lot like a vertical stretch. So this would be horizontal shrink by a factor of 1/8. All right. So that's it for that. If you're working through your assignment and you kind of forget the rules for, you know, all of our transformations, first go back to here. I like that they give examples as well. That's really helpful. If you get lost, just ask me. I'll be happy to help out. All right, flip it over. Now we're going to be writing transformations. I would like you to try A and B on your own here. By the way, the g of x at the top here, we wrote that at the bottom of the previous page, so don't worry about that. So try A and B. You can use the chart from the previous page. Actually, no, let's do A together because I want to remind you of something. If you are starting with your parent function, cube root of x, and you're writing a new function, g of x, but there are two things happening, there has to be a middle function as well. So it's like a two-stage deal here. So we can't just go straight into writing our answer. We have to do the first transformation and then do the second one. So the first one is going to be a vertical shrink by a factor of 1/6, followed by a translation 3 units left. Now, that's not actually going to change anything if you do them both at the same time, but sometimes it can. So that's why we're going to do them separately. So we can't write g of x next. So I'm going to say, let's go to h of x for our first transformation, even though it doesn't tell us anything about h of x. H is another common letter along with g and f when we're talking about functions. So if we have a vertical shrink by a factor of 1/6, what's that going to look like with the parent function when we apply it to this? What's that? If it was a horizontal shrink, yes. Yeah. So vertical is going to happen outside the group. So it'd be 1/6 times the cube root of x. All right. And then we're going to follow that up with a translation of 3 units to the left. So we're going to have g of x is equal to 1/6 times the cube root of what? X plus 3. Good. And that will be our answer here. All right. Now try B on your own. Actually, because we're starting with the parent function, you can actually apply both of the transformations at the same time. If we didn't start with the parent function, we'd have to do them separately because we're starting with the parent function, you can actually just do them both at the same time. Well, everybody's here today. Cool. So if you want, you can apply both of these at the same time. I'll just go ahead and do that as well. So g of x, any volunteers for an answer here? Reflection over the x-axis, is that a vertical or a horizontal? So the x-axis is here, but if you reflect over the x-axis, that's a vertical reflection. So does that happen outside or inside the radical? Outside, all right. So it'll be the opposite of the square root of x. And then we're going up 5. So plus 5, outside or inside? Outside. Nice. There it is. So it's the opposite of the square root of x plus 5. So basically, you take your regular square root, and then you would flip it upside down, so it'll look like this, but then you'd have to move it up. So it'll be kind of up and then an upside down. If you want to check it on your calculator, you're welcome to do that too. All right. Now, next we're going to be graphing a parabola. However, this parabola is not like other parabolas you've seen because parabolas don't just exist right side up or upside down. Parabolas can exist on their side. They're not functions, but they can exist on their side. The reason why they're not functions is because you get stacked values for the same value of x, which doesn't make it a function, but it is a graph and it is a parabola, and we can graph it, and we're going to. So most calculators make you enter functions beginning with y. So to graph parabolas and circles, this is going to apply to the next problem as well in the back. I think we only have 2 problems left. Yeah, we're almost done. To get these on a graphing calculator, you have to first solve the equations for y to obtain radical functions. So when you graph a sideways parabola or a circle, you're going to end up typing that in as 2 separate functions on your graphing calculator. And then graph both functions. And the reason why we're going to end up with 2 functions is because to get y by itself, we're going to end up having to square root. And when you square root, you get both a positive and a negative number, which will give us 2 separate functions to graph. So the 2 functions will be separate, but the one function or the one graph that it creates will not be a function, if that makes sense. All right. So we're going to use a graphing calculator to graph this, but we can't graph it like this. Now, Desmos might allow us to do that. I think Desmos probably would do this. It would probably be fine with you typing in 1/2 y squared equals x. In fact, let me just do a double check here. So here's the Desmos graphing calculator. It's a really handy thing. If you ever use it on a phone, it's great because it functions almost exactly like these. It's just a little bit harder to type just because the buttons are really small. But if we wanted to, I bet we could go ahead and just put this in. Let's see, 1/2 and then y squared equals x. Yeah, there it is. Look at that. That's kind of cool. So this one, Desmos doesn't have any problem with it. The unfortunate thing, well, not really unfortunate, the thing about a test or a quiz is that you're not going to be allowed to use Desmos because it connects to the internet. So we don't have that problem with Desmos, but we do with our graphing calculators. There's no way to do a y squared equals x. So what we need to do is get y by itself. So we want to undo the 1/2 over here. What do we have to do first? What's that? Yeah, multiply by 2. Multiply both sides by the reciprocal of the fraction. In this case, it's 2. So that'll cancel, which will give us y squared equals 2x. All right. And then the last thing, there's only 2 steps here. The last thing we need to do is square root both sides. And so that'll give us y equals plus or minus the square root of 2x. Which gives us 2 functions. One of the functions will be y equals the square root of 2x. The other one will be y equals the opposite of the square root of 2x. So those 2 things are the same as the original, except these 2 will be understood by your calculator where the original would not. So if we head to our calculators, we'll go back to our y equals. I'm going to clear that out. And I'm actually going to change red over here to blue, just so I can match it. That way it'll look like one cohesive graph. You can adjust the colors by scrolling to the left and hitting enter and then cycling through the colors until you find the one you want. So here we go. Square root of 2x and the opposite of the square root of 2x. And if we graph that, it gives us our 2 separate functions that when put together don't make a function, but they do make a sideways parabola. All right, now we're going to be talking about the domain and the range. So possible values of x here. Actually, what else does it want us to say? It says identify the vertex. Okay, so where's the vertex at here? 0, 0. Okay. Actually, we need points, don't we? Because we need to graph this on our paper as well. So why don't you hit the blue button, the second button, and then hit graph, and it'll just take you to your table of values. And it looks like we're going with 0 through 10. 0 through 10. There we go. So you got the point 0, 0. Since I'm left-handed, that'll make it a little bit more sense. We'll have 1 and then up 1.41, so almost 1.5, and then over 1 and down about 1.41, almost -1.5. If you want to turn it on its side and graph it like a regular parabola, that's fine too. Let's see, 2, 2, that's convenient, and then 2, -2, about like that. Let's see, 3, 2.45. Almost 2.5, almost -2.5, 2.82 for 4, a bit higher there, -2.82 about there. Let's see, 3.16 and -3.16, so that's about here and here for 5. 3.46, so that's about 3.5, and about -3.5. What else? Where are we at now? 7. 3.75, that's about here, and about here. 8, 4, 8, -4, that's easy. 9, 4.25, so about a quarter of the way up there, and about a quarter of the way down over here. And then about +4.5 and about -4.5. So that's generally about what it's going to look like. It's a lot of detail. And so graphing parabolas, generally what I'll do is I'll start at the vertex when I graph, just so I can get the shape of the curve the way it needs to be. And then we can go ahead and just put it all the way through. Like that. And we'll get it about as smooth as we can. Not bad. All right. So there's our graph. We set our vertexes at 0, 0. So I'm just going to say V 0, 0. All right. What direction does this parabola open? Opens to the right, yeah. So opens to the right, where before we would usually say opens up or opens down, but because it's a sideways parabola, it's going to open left or right. This one opens to the right. How about the domain? X values, what are we looking at here? Greater than or equal to 0. Smallest x value is 0. Largest x value is as large as you want it. How about our range? What is it? All real numbers, yeah, because it's going to go up forever and down forever. Nice. Cool. So that's it for that. We're definitely doing different things today, but they're different in a way that is very familiar with stuff you've done before, I think. So I'm hoping this isn't feeling too crazy. Any questions on this page before we look at our circle? Cool. Oh, we're going to get a decent amount of time to work today too. Nice. So flip it over. Let's finish these up. Like I said, there's kind of a lot of new things in here, but the new things aren't super terrible, and we're able to move here pretty quickly. So this is good. Same idea on example 6 as example 5. We are needing to get y by itself in order to get these on our graphing calculators. Again, if you want to use Desmos, you can just type that in and it'll show you what the circle looks like, which is awesome. But you still need to know how to use your calculators, which means you have to be able to solve for y. So if we're solving for y, the first thing we need to do is get rid of that x squared. So subtract x squared from both sides. And y squared equals, now I'm a big fan of keeping my variable before my number. So I'm going to say the opposite of x squared plus 16. If you said 16 minus x squared, I don't have any problem with that. But I'm going to keep it like that. Now, our last step here is to square root both sides. Now, the opposite of x squared, that is not a problem in terms of having a real number solution because we don't know what x is. So that doesn't cause any problems for us. So we're going to end up with y is equal to positive or negative square root of the opposite of x plus 16, x squared plus 16, sorry. Those do not square root. Because we're square rooting a sum, we can't actually square root that. If this was the square root of like 16 times x squared, then yeah, it would be positive or negative 4x. But because these are separated by a plus, these do not square root together or anything like that. There's nothing we can do about square rooting this, so we have to keep it under our radical. So this is going to turn into y equals the square root of the opposite of x squared plus 16, and y is equal to the opposite of the square root of the opposite of x squared plus 16. It's a lot of opposites. Opposite. All right, now graphing a circle generally is going to be maybe a little bit easier because the points are going to be a little more obvious to find versus the sideways parabola. Question? No. And it's because these are connected by addition and not multiplication. So because they're separate, we can't do anything about simplifying that. The only time, like the rules that we learned with like our like radical terms and things like that, those only work if things are being multiplied together as opposed to being added or subtracted. So nothing we can do about that. We just got to write it like this. Yeah. So if it was like 16x squared multiplied together, it would square root to 4x. But because it's 16 and x squared separated by addition, then nothing we can do. All right, so we're going to go ahead and put both of those in. Square root of the opposite of x squared plus 16, and the opposite, oops, no, I'll just go up here and do the opposite one, for y1. The opposite of the square root of opposite x squared plus 16. And then we'll graph it and take a look. Now that is a circle. Doesn't really look like one because of the way the screen is showing it to us, but it is a circle. If you want to actually make it a circle or make it look more like a circle, you can push the button that says zoom right in the middle. And instead of, right now you're probably on Z standard. If you go to Z square, it'll change the scale how X and Y relate to each other, but it'll make it more of a square shape. And so it'll be even in both directions, which makes it much more circular looking when you do it that way. So if you go to Z squared, there you go. Now, I'm not sure why it's not showing the connection, but those do connect. If you go back to, here, let me go back to Desmos real quick. If we head back to Desmos and I just, let's see, clear this out, we're looking at x squared plus y squared equals 16. So x squared plus y squared equals 16. You can see that it does connect through the x-axis, even though on the graphing calculator, it doesn't show that, it's still there. So quick question here. What are the x-intercepts on the x-axis? 4 and -4, yeah. What about the y-intercepts? 4 and -4 again, yeah. So this is where circles sometimes are a little bit easier to get on your paper because all you need to do is figure out where the center of your circle is.
Please, can we release the girls basketball team, both varsity and JV? Please make sure you go to the attendance office and check out prior to getting on the bus.
Figure out where the center of your circle is. Basically, use the radius from there. The radius is 4. And then try as best as you can to make a circle out of it. Now, it's not necessarily going to be an easy thing to do, especially the first couple times you work through it. In fact, I'm going to start with a pencil before I put pen on mine. Because making a nice circle is not super easy. In fact, I'm going to go to my table of values and try to get some more points on here. So let's see, if x equals 0, I'm going to go back to x equals -4. Let's see, where's another, we don't have any great numbers on here. So let's see, -3 is -2.65 and 2.65. So maybe about there and there. I'm just being more detail oriented than I would expect you to be, but I don't know. I like my things to look nice when I'm working on them. So let's see. 3.46, that's about 3.5 here. And about -3.5 here. And then 3.87, 3.88, that'll be about there and about there. And then we can just reflect all those as well. Not like that. Okay. We'll see how that goes. Let's start down here. All right. So there's our circle. Got a few extra points on there. Just makes it look a little bit nicer if you can get a couple extra points. Again, I don't really care how perfect your circle looks, but for myself, I like being fairly detail oriented and making it look as nice as I can. So that's a circle-ish. Okay. So that's our answer there. There's our graph. Now we just got a few more things to talk about. What is the radius of this circle? How far is it from the edge to the center? 4. All right, so the radius is 4. I already asked you what the x-intercepts were, and you said -4 and 4. So x-intercepts would be, we can just do it this way, -4, 4. We can use set notation. Using the braces, by the way, with set notation just means you're talking about the same value. So we can do the same thing for y as well, because the y-intercepts were both -4 and +4 as well. So we can do set notation here, -4 and 4. All right. Domain and range. This one's a little bit more interesting with the domain and the range. So go ahead and get those in there. Let's take a look now at our x values. What are we talking about with x values here? What are the possible x values? X is greater than or equal to -4 and less than or equal to +4. Exactly. And so the way to write that would be to use a compound inequality. And the way that I usually show this is I say, all right, put your lower extreme on the left, put your upper extreme on the right, put the variable you're talking about in the center, x, and then fill in with less than or equal symbols in between each -4 and x and -4. So less than or equal to here, less than or equal to here. So x is greater than or equal to -4, but x is also less than or equal to +4. And in the case of the range, it's the exact same thing, but the only difference is we're going to have a y in the middle instead of an x. So we'll say -4, +4, put the y in the middle, less than or equal to, less than or equal to, and that's it. Okay. That's all I got for you for 5.3. So we are officially done with the first half of chapter 5. So that means we will start in on our chapter 5, part 1 test review tomorrow. You'll get that tomorrow. We'll work on that tomorrow and Thursday, and we will take that chapter 5, part 1 test on Friday.